Now that we've seen a couple examples of how to take the Laplace transform, we want to focus on how to take the inverse Laplace transform. So taking a step back and reminding us of sort of our process here, we're transforming to the S domain. We're going to do all of our analysis in there because remember we're going to be doing algebra instead of calculus. And once we finish our analysis, we're going to transform back to the time domain to have our final solution in time. So sort of focusing on that inverse transform step, after we've done all of this analysis in the S domain, what we're going to have is some rational function of S. And so what I have here is a generalized form of what that function might look like. We know that we can break it up in terms of a numerator and a denominator polynomial. And our numerator polynomial is seen here. We have a sub n times s to the power of n, and so on and so forth, all the way down to where we have an a naught. And similar thing for our denominator. And so basically all of these a's and b's here, so our b's and our a's are just going to be some real valued constant. So a and b terms are real valued constants. So then the other terms, of course, we can see our s's, and the s's are raised to some power. So we notice here we have s to the n minus 1, and here is s to the 1, and then of course we'd have s to the 0, which doesn't show up as anything because that's just 1. And in the denominator we have m minus 1, and here is an implied 1, and so forth. And so these n and m values are going to be positive integers. So n and m, which are our exponents, are going to just be positive integers. And so our basic sort of approach to finding this inverse transform is, remember, we don't want to use that complicated equation that we solved previously. So we don't want to use, and so it was basically an integral and it had some nasty limits with some complex numbers. So we don't want to use our complex equation. We can, but we're going to look at an easier way to do this. So instead of doing that, what we're going to do is we're going to follow a two-step process. So the first step in this process is we're going to decompose this generalized function into smaller pieces. So decompose f of s into simple terms. And so the way we're going to do that is using something called partial fraction expansion. So partial fraction expansion. And so that's what we're going to focus on in a lot of the following videos. And sometimes you'll see this abbreviated as PFE. So this is sort of going to be the key technique for taking inverse Laplace transforms. So once we have decomposed this complicated f of s into simpler terms, our second step is then just going to be to use a table of transform pairs. So use table of Laplace transform pairs, and we can just inverse transform from inspection. And so remember, we might need to take into account our operational transforms as well as our functional transforms. So we're using this to transform each of those simplified components. And so the table of Laplace transform pairs, I might have mentioned this before, but I'll go ahead and say again, it's on page 685 in your textbook, but I also have a handout posted in Canvas. And so I think it's sometimes hard to grasp when we're talking about general equations and things of this nature here, but we're going to look at several examples to kind of help this make a little more sense. One thing that we want to note, a condition that needs to be met for our f of s in order for this process to work, is that this partial fraction expansion, for partial fraction expansion to work, our f of s has to be a proper rational function. So for partial fraction expansion to work, to decompose our f of s must be a proper rational function. And so what does that mean in terms of our general equation up here? So that means that the exponent m in our denominator has to be larger than the largest exponent in our numerator, n. So what that means is that m has to be greater than n. And so there's going to be a supplemental video that you can watch as far as to see how do we deal with the case if we do not have a proper rational function. And it's pretty simple. We basically just have to do long division with our function f of s. But the main thing to take away from this video, and we're going to focus on this more in later videos, is this two-step process of partial fraction expansion to decompose our general equation and then using Laplace transform pairs to get back to our time domain solution.